Okay, today we're going to discuss logarithmic functions. In the last lesson we discussed exponential functions. Recall that 2 to the x look like this. Example. It was one that was always increasing. It went through the point 0, 1, and the domain was all real numbers, and the range is everything from 0 to infinity. So there's 2 to the x, and also it's a one-to-one function, meaning that, recall what that meant, it means it satisfies the horizontal line test. Any horizontal line is going to hit it at just one point at a time, which means that given any y value, there's exactly one x value that gets taken to it, and because of that, it has an inverse. And recall how we get the inverse. The inverse is gained by just taking this thing and reflecting it about the line y equal x. So if you do that, you get a function that looks like this. See how I can do it the best way? How about something like this? Something like that. It's going to keep getting larger and larger there, and keep going down towards negative infinity here. And this inverse of 2 to the x, we give the name log base 2 of x. That's, by definition, the inverse function of this one. And let's look and see what some of the properties of this are. This has the point 1, 0 on it, which means the logarithm of 1 is equal to 0. This has the point 2, 1. And so, 1, 2. And so this one here has the point 2, 1 on it. Okay, this one would have the point 3, 8. Hard to get it up there. And so this one here would have the point 8, 3. Okay, they undo each other. One way of showing that they undo each other is by, again, recalling what the definition of an inverse function is. It's something which undoes the original one. So in other words, the log base 2 of 2 to the x, since they undo each other, that just gives you your x back again. So log base 2 of 2 to the 5th power is just going to be equal to 5. Log base 2 of 2 cubed is going to be equal to 3. This is equal to 2 cubed right there, and so on. And as we also mentioned, since this is the inverse of this, 2 to the x is the inverse of this, which means 2 to the log base 2 of x is equal to x. They undo each other. And the other thing to notice right off the bat is that, again, as we noted, is true in general for inverse functions, the domain of the log base 2 of x is equal to the range of 2 to the x and conversely the range of log base 2 of x is equal to the domain of 2 to the x. Notice the domain of this one is just everything from all the positive values, and that was the range of this one, and the range of this one is everything, and that was the domain of this one. Okay, so they undo each other like that. Okay, so that's true for 2 to the x. It would be true for 3 to the x, 10 to the x. All those functions have very similar same ideas. Okay, So now let's look at the other one that I mentioned last time, and that is e to the x, okay? And this is the one we're going to really concentrate on from now on, because once you know e to the x, all the other ones kind of are easy outgrowths of e to the x. So here, same sort of function here, y is equal to e to the x. E was this number between 2 and 3, recall? And then if we draw the inverse of that, it's going to have the same sort of shape again. It's just going to be log base e rather than base 2. So that's going to be log base e. And since this is such an important number and such an important graph along with this one, we actually give it its own special name. We call it the ln of x. ln of x stands for the natural logarithm. It's natural because, as I showed last time, e just kind of pops up all over the place in mathematics. So it's kind of a natural number, hence we call this the natural logarithm. But it's just log base e is all it is. And so the same ideas hold here as before. This could be log base e, or I could just call it the ln of x. The ln of e to the x is just x. They undo each other. Similarly, e to the ln of x, they undo each other. So everything just undoes the inverse. And similarly, the domain of the ln of x is equal to the range of e to the x, and the range of the ln of x is equal to the domain of e to the x. And notice it's also a one-to-one function, and those are the most important properties of the ln of x right there. Those are most of them, but there are a couple other very important properties of the ln of x. Here they are. And this is true again for all logarithms, but I'm going to concentrate on the ln of x now. The ln of x times y turns out to be equal to the ln of x plus the ln of y. Very interesting. Easy to get confused. Here they're being multiplied, here they're being added. And so the ln of 2 times 7 is equal to the ln of 2 plus the ln of 7. Okay? Let's prove that. We won't do too many proofs in this course, but this was one worth proving. Here's the proof for it. Notice that e to the ln of x plus y, they undo each other. E to the ln of anything just gives you that thing back. So this is equal to x plus y. And then x we can write as e to the ln of x and y we can write as e to the ln of y. Oops, something was wrong. I was trying to figure it out. This should have been times right there. Okay, very good. Okay, let's change that as we go. Okay, we want to start off with ln of x times y. Okay, very good. Ln of x times y. So that's going to be x times y there, because e and the ln undo each other. And then this is going to be times right here. Okay, x is equal to e to the ln of x, y is equal to e to the ln of y. And now what do we know is true about properties of exponents? if you have e to one thing times e to the other thing, that's e to the sum of those two. So you get that right there. And so here's our final result, is that e to the ln of x times y is equal to that. And since e to one thing is equal to e to the other thing, notice that e is a one-to-one function. So if e to one thing is equal to e to the other, if the functional values are the same, that means that those two things have to be the same. It's a one-to-one function, so if e to this thing is equal to e to this thing, that means that these two things have to be the same. So in other words, the ln of x times y is equal to the ln of x plus the ln of y. So we have that, and then as a derivative of, well, let me just go from there. So we have that, and then here's another property. This is property number 1. Here's property number 2. It's that the ln of x to the y power is equal to y times the ln of x. So that's another very unique property that logarithms have. And let's go ahead and prove this one. We prove it the same way. We start with e to the ln of x to the y power. And that is equal to x to the y power, because these two things undo each other. And then, if you want to, you can write x as e to the ln of x, right? That's what x is. X is e to the ln of x. So we have all of that to the y power. And now, what's one of those other properties of exponents? If you have some base to one power all raised to another power, that is the base to the product of these two things. So that's equal to e to the y times the ln of x. And now, same as before, since e is a one-to-one function, if e to one thing is equal to e to the other thing, the only way that can happen is if these two things are the same. So in other words, this implies that the ln of x to the y is equal to y times the ln of x. So there's two very, very important and very unique properties of the logarithm. Okay, so those are ones to know. Once you have those, then you can get other ones as well. For example, let's just write this one down. The ln of x divided by y is equal to what? That's equal to the ln of x times y to the negative 1 power. And because if you bring this over the line, it's going to be the negative 1 power. And that's, according to this rule now, the ln of x plus the ln of y to the negative 1 power. And then you can use this property, bring the negative 1 power down, and you get the ln of x minus the ln of y. So if you multiply these in here, you add the logarithms. If you divide these in here, then you subtract the logarithms. So those are important properties of the logarithm right there. So let's just do, starting at this point in the course now, I'm going to start doing a few more examples just to make sure that you, the viewer, understands things. And as I suggested before, you're welcome to turn off the video and see if you can figure them out on your own. Let's first do this one. Simplify e to the 12th minus e to the 6th divided by e cubed. Okay, how could that be simplified? Well, I like to give this problem just because it just tests to see whether people understand the rules of exponents and logarithms or not, or so. And so here's what you can do with this one. You can factor an e to the 6th out of both of these, and you're going to be left with an e to the 6th minus 1, all divided by e cubed. And now that things are being multiplied, here you have 6 e's all multiplied by each other. Here you have 3 e's all multiplied by each other. You can cancel 3 of those, and you're left with e cubed times the quantity e to the 6th minus 1 over 1. I guess you don't even need that. Okay, so that's as far as you can simplify that one. How about this one? The natural log of 12 minus the natural log of 6 divided by the natural log of 3. Okay, how can you simplify that one? Well, we can use property that we just learned about logarithms. We can write this as the ln of 12 divided by 6, all divided by the ln of 3. And of course, that's the ln of 2 divided by the ln of 3. And that's as far as we go. Okay, there's no rule that tells us anything about ln's. That's as far as we can go right there. Okay, so there's a couple examples. Let's try maybe one more problem involving inverses. How about this one? Find the inverse of f of x is equal to 5 minus e to the 3x. Okay, how would you find the inverse of that? Well, recall what we mentioned before. You first put a y right there. Second step is to interchange the x and the y. Like that. And the third step, the substantial one, is to now solve it for y. So how do we solve this for y? First thing I can do is, I'd rather have this be positive. So I'm going to bring this to this side and bring the x to this side. So I'm going to write it as e to the 3y is equal to 5 minus x. Now, I need to get this y down. It's up there in the exponential position. How do I get it down? I can get it down by taking the natural logarithm of both sides. So if I take the natural logarithm of this, that's going to be equal to the natural logarithm of this. Those two things are equal, so the log of them are equal. The natural log and the e, they undo each other. So the natural log of e to anything is just that thing. And then finally, divide by 3. And there you have the inverse. Okay? Let's try 2 more problems. Graphing. What about this one? Let's try, let's do this one. Sketch the graph. Here's one of my favorite problems. Of the absolute value of the ln of the absolute value of x. Sketch the graph of that. What does that look like? Okay, well, let's think about it. I always start with the basic one. What's the ln of x look like? It looks like that. It only accepts positive numbers. Okay, so it only accepts positive numbers starting, and then 1 goes to 0, and this keeps going up higher and higher like that. Okay, so that's the ln of x. So given that, what's this one going to look like? Well, think about this one. This will also accept negative numbers because now I can throw in any negative number I want, and before the ln sees it, it's going to become positive. And what does the ln do when it sees a positive number? It does this right here. So if I wanted to graph that for positive values, it's going to give me the same thing as before, but now also for negative values, it's going to give me the same thing on this side because ln will see positive values, so it's going to look like that, very roughly. Okay? Okay? There's the ln of the absolute value of x. Notice that this is an even function, because if I put in either x or negative x there, I get exactly the same thing out. So this is an even function right there. So there's that one. Now, what happens if I graph the absolute value of that? What does the absolute value of a function do? It takes anything here which is negative and it makes it positive. So all this part of the function is already positive, so the absolute value will keep it as is, but all this part which is negative, this will now turn positive. So it's going to look something like this. This part's going to be the same, this part's going to be the same, okay? And this part, which did go down, is now going to go up. It's going to look something like this, and similarly this one is going to look something like that. So there is, again, very roughly, go to Decimus. Remember Decimus? And you'll get a nicer picture of the graph. Let's try one more. Let's do one with exponential. How about this one? Let's take e to the negative x and multiply it by, say, 2 or negative 2 and add 5 to it, and then take the absolute value. Let's do all those things and see once what happens. Okay? So here's e to the x right there. Okay? E to the negative x is going to be the flip. It's going to look like this. Because recall when we had this function right here, this was f of x, and I said, what does f of negative x do? And it flipped it over. We had this thing down here, and we had this thing up here. It flips it over the y-axis, because what was positive becomes negative, and what was negative becomes positive. So similarly, this one is going to look like this. Another way of seeing that it's going to look like this is to realize that e to the negative x is 1 over e to the x. So as e to the x gets big, 1 over that's going to get small. As this gets small, 1 over that's going to get big. So this right here is e to the negative x. Okay? And now what happens if I multiply that by 2? If I multiply it by 2, it's going to be 2 units up, 2 units higher. So instead of going through the point 0, 1, it's going to go through the point 0, 2. And these will still be going down to 0. It's just that they'll be 2 units higher, and those are not 2 units higher, but twice as high. That'll be okay. Let's see. So what did I just say? This is the point 0, 2. So now we have this one, and where do we go from there? Now we want to take the negative of this. We want negative 2 times this. So what happens when you take the negative of a function? Everything which is positive becomes negative. So this is going to be down here now. Looks something like that. Here's the point 0, -2. Okay, so it looks like that. And what happens after we do that? Now we add 5 to it. What happens when you add 5 to a function? We take this function, we add 5, which means before we graph any of the points, any of the y values, we add 5 to each one. So that shifts the whole thing up 5 units. So instead of having a y-intercept of -2, it's going to have a y-intercept of 3. And instead of leveling off at 0, it's going to level off at 5. So it'll look something like that. And then finally, now we want the absolute value of it. So what does that do? Remember the absolute value, anything which is positive stays positive. So all these values of the function are positive, so the absolute value doesn't change them at all. But anything which is negative, the absolute value takes the opposite of it. It turns them into a positive. So here's my function that's positive, and now this negative part becomes positive. So it looks something like that. So this is all good to do. This function here, probably never run into it. This function here, though, is very typical, especially if you look at the portion just from positive x's on. Okay? There are a lot of things in the natural world which behave kind of like this. They start at a certain value and then they kind of asymptotically approach some other value. You can think of pulling something out of the cold and you bring it inside, and this is the inside temperature and this is the outside temperature, and it's just going to kind of gradually increase to the inside temperature. And it's going to start off increasing pretty fast, but then as you get closer and closer to the inside temperature, it just kind of levels off. So lots of things like that. So anyway, there's a review of both exponential and logarithmic functions. In the next lesson, we get into limits, which is basically the guts of calculus right there.